Hi, good evening, Aditi. Uh, it's 6 p.m., but not many people have joined. So we will wait for a few more minutes before we begin. Thank you. Hi, Narud. We'll just wait for a few more minutes before we begin to allow more people to join.
Yeah, sure. Hi, Sourav.
Hi, we'll begin in, say, 10 minutes or so. Good evening and welcome to the second live session for the course AE03 Computational Science and Engineering. The instructor for this course is Professor Ashok Dey from the Department of Aerospace Engineering at the IIT Kanpur. And I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay, and I'll be your tutor for this course. So this is week two. We have already introduced ourselves. And the way we'll conduct this session is we'll recapitulate some of the key concepts that were covered in the lectures for this week, and then we'll solve a few illustrative problems to elaborate those concepts and hopefully to enable you to solve your assignments better. Again, for seamless communication, I request that you raise your hand and then I'll call out your name and only then you unmute and speak. Otherwise, you remain unmuted at all times. Otherwise, you remain muted at all times. We looked at a few, in fact, quite a few concepts from vectors, vector spaces, vector subspaces over the last week, and I realized that some of those were abstract and not very intuitive in the first place. So today I've compiled a few of the key ideas that we must remember and carry forward on our journey through this course. Uh, some of this content has been borrowed from the textbook by Professor Gilbert Strang. Uh, You may refer to it for more clarifications or for in-depth proofs and treatment of this content. So we'll just go over the concepts once more before we solve a few examples. So first a recap of the vector space itself. So the standard n-dimensional space Rn contains all the real column vectors with n components. Um, Hi, I would again request everyone to remain muted at all times unless you have a question. In which case, I'll request you to raise your hand first, and then we can discuss a point. Thank you. Yes. So the standard n-dimensional space Rn contains all real column vectors with n components. In fact, last week we had a discussion where whenever I'm denoting, say, a real vector space by this letter R, and it has this superscript over it. What does the superscript even mean? So turns out this is the number of say the dimensions. So when we are working in three-dimensional space, we call it R3. When I'm working in only a two-dimensional space, so say a plane, the set containing all real vectors in this space shall be R2. Similarly, when I'm working in an n-dimensional space, the vector space shall be referred to as Rn. So R refers to real and n refers to the dimension. And currently we are working only with real vectors, but as we progress further down along this course, we will be introduced hopefully to imaginary and complex vectors as well. Again, some important properties of the vector spaces is that if V and W are in the vector spaces, that is, if there are two elements of the vector space set, then every combination CV plus DW must again be in S. This is a definition which qualifies any vector space or any space S to be a vector space in the very first place. So usually this is broken down into two, like we have here. So first is that the any scalar multiple of the vector should be in the same subspace, and the sum of any two elements of the space must again lie in the same space. They are combined together in this fashion. So any linear combination of any two elements of the space must lie in the same space for the space to qualify as a vector space. Again, the vectors in S can be matrices or functions of X. We went over this last week as to how the intuitive idea we have developed, say in a physics course, is of vectors being quantities with magnitudes, directions, and a sense. However, that need not be the case always, and in fact, a vector can be generalized to be any quantity we want it to be. It can simply be an ordered, say, n tuple. So you have these components, and this need not have any physical meaning, or at least a perceptible physical meaning as such, or it can even be a set, and that is the treatment we are following in this course. So vector spaces are actually sets. Vectors are elements of those sets that obey certain laws. Again, the one point space Z consists of x equals to 0. So this is just the zero element. In 1D space, it will be only 0. In R2, this can be 0, 0. In R3, it will have one added dimension and so on. So in Rn, you will have an n cross 1 zero vector and so on. And in this text, it has been referred by Z. Again, a subspace of Rn is a vector space inside Rn. Column space of A contains all combinations of the columns of A. So we had another query last week where the ideas of null space, column space, row space maybe was not so clear. We'll try to go over it again this week. But fundamentally, or from the definition point of view, the column space simply consists of all the combinations of A. When it says combinations, of course, it means linear combinations. So, say you have a vector. So, any matrix, say A11, A12, A13. It need not even be square. I'm just writing as an example. So, you have these three columns C1, C2, and C3. So, any linear combination of these, say AC1 plus BC2 plus C, sorry, not a very good so prefix, DC3. So any linear combination of this, uh, the space which contains all of these linear combinations is actually the column space. So it is actually the space which is spanned by the columns of A. And what does span exactly mean? We'll look at in the upcoming slide. Again, the column space contains all the vectors AX such that AX equals to B is solvable when B is in column space of A. This is another important concept to look at and remember when we are trying to solve these linear systems, that the system Ax equals to B will, I mean, have a solution in the very first place only when this right hand side vector B will lie in the column space of A. Should B not lie in the column space of A, then the system will not have any solutions. Again, the definition of subspace is that a subspace of any given vector space is a set of vectors including zero, and sometimes zero becomes very important. We'll see when that satisfies two requirements, such that if V and W are any two vectors in the subspace, and C being any scalar, then the any linear combination of V plus W is also in the subspace, and again any scalar multiple of V or W is again subspace. These rigorous definitions will be used to investigate whether any given uh, space is indeed a vector subspace or not. We also looked at a couple of examples on this in the past week. Again, the definition of column space suggests that it consists of all linear combinations of the columns, and the combinations are all the possible vectors AX, and they fill or span the column space of CA. Again, when we are solving Ax equals to B, we are actually trying to express B as a combination of the columns. And the right side B has to necessarily lie in the column space, or there is no solution. Again, this is again say defined here as the system Ax equals to B is solvable if and only if B is in the column space of A. So this can be used as a test before we actually get down to solve a system. We check whether B indeed lies in the column space or not, and if it can be easily or analytically seen that B does not lie in the column space, then we need not even look for a solution because, well, it does not exist. Now moving on to the null space. The null space, often denoted by say n for any matrix A, in Rn contains all solutions x to Ax equals 0. So for the homogeneous system, the RHS is 0. For non-homogeneous system, of course, we know that it's equals to B. So for all solutions of x which fit this equation x equals to 0 comprise of the null space. So, obviously you would find that one very obvious solution is the zero vector, which will necessarily and or trivially satisfy this. So the null space will always contain the zero vector, and it might or might not have other elements in it. So this of course includes x equals 0, and elimination from our starting matrix A to any upper triangular matrix U to any reduced row echelon form R does not change the null space. So the null space remains unchanged when we perform, say, the elementary row operations on our matrices. However, the column space does change, and this is an important point to note. So, because often you will find that, say, the operations that we perform on rows, maybe we can perform some similar operations on columns and end up with the same result. While that might be true for certain sets of operations, however, it is to note that the column space may change, and in fact does mostly change when you are performing elementary row operations or elimination on a given matrix. However, the null space remains unchanged. Again, the reduced row echelon form R, which we obtain via Gauss-Jordan elimination. We looked at a few example of one example of Gauss-Jordan elimination in the past week, and this reduced row echelon form has all pivots equals to 1 with zeros above and below. What are pivots? So say when we have any matrix, say 1, 2, 3, 4, 1, 1, 1, 2, 3, 4, 5, for instance. So when we perform elementary row operations, what we intend to do is say use one of the rows and eliminate these elements here to form, sorry, not this one, to form an upper triangular matrix. And necessarily, to be able to do that, we must have some, so these diagonal elements must not be zero. And the more diagonal elements we have, the better it is. However, it may happen that in some cases, the diagonal elements may turn out to be zero, in which case they cease to be pivots. However, uh, in the cases when they are not zero, we use these elements to eliminate the elements in the same column in the rows below, sometimes even above. And these are referred to as pivot elements. The column containing such an element would be referred to as a pivot column. And as we'll see, or as we might have already observed in the lectures, the number of pivots, in fact, equals the rank of the matrix. If any column J of the row reduced echelon form is free, that is, it does not have any pivot, then there is a special solution to x equal to 0. The number of pivots is equal to the number of non-zero rows in R. This is the definition we used in the past week to define the rank. They are equivalent, and this equals the rank R of the matrix. And then there are n minus R free columns. Should it be a full rank matrix, then there will be no free columns because n minus R will equal 0. And every matrix with m less than n, so the number of rows less than the number of columns, has non-zero solutions to Ax equals 0 in its null space. So its null space will have elements in addition to the zero vector. And again, the null space Na consists of all solutions to x equals 0, and these vectors of x lie in Rn. So the space here, the dimension of this is actually the equal to the number of columns. Now I have, say, a simple matrix here where we'll try to illustrate the column space and the null space with. So say the matrix I just used, say A equals 1, 2, 3, 4, 1, 1, 1, 1, and 2, 3, 4, 5. So I have deliberately not chosen a square matrix to keep it more general. However, the matrix still is pretty simple, but then it helps to illustrate the concepts we are trying to look at. And again, when we talk of the column space, the key idea which brought us to this column space in the first place is solving the linear system x equals b. And then the question we are trying to answer is which b's allow the system to be solved. Is there any B which does? And if yes, I mean, what is the restriction on that B, or what is the criteria which allows it for to solve this system? So say for AX to B, it will be something like 1, 2, 3, 4, 2, 3, 4, 5. This is a 4 cross 3. And so here we'll have only three elements, say x1, x2, x3, 3 cross 1, and again B will be 4 cross 1. So say B1, B2, B3, B4. So this is allowed as per matrix multiplication. And in the definitions, we already saw how this B should be uh, in the column space of A. So if I just put one of the columns, say 1, 2, 3, 4, then what X do I end up with? So in such a case, X will in fact be 1, 0, 0. And the way to think about this, just from inspection, is that so this is equal to x1 times this matrix 1, 2, 3, 4, 1, 1, 1, 2, 3, 4, 5 plus x2 times again 1, 2, 3, 4, 1, 1, 1, 1 and 2, 3, 4, 5 plus x3 times into 3, 4, 1, 1, 2, 3, 4, 5. And also it is equal to 1, 1, 2 times x1, x2, x3 plus 2, 1, 3 times. So taking each row at a time. And similarly for the fourth row. And you can try doing this on your own and you'll see this that it works out. So there are multiple ways to visualize matrix multiplication. This is one of those. And thus, so the way to look at it is I have just taken the first column on the RHS. So this. So if I just took, say, the column 1 and multiplied the others by 0, I'll end up with the RHS. And so by just by inspection, I can say that x1 equals 0. Sorry, x1 equals 1, x2 equals 0, and x3 equals 0. So this can be one solution. Say for the same matrix, if so I'm looking at the column space. So I want solutions and I'm looking at the B's which allow this solution to be this system to be solved. We already know they must lie in the column space. So say I select some other column 1, 1, 1, 1. For this, the corresponding solution shall be 0, 1, 0. Just how we saw. So we just need the second column. If we multiply the other two columns by 0, we end up with the RHS. And this, uh, so this is one way to visualize that x equals b can be solved only when b is lies in the column space of A. Uh, the proof of this is out of the concept, out of the scope of this current course, especially these sessions. But again, you can refer to the textbooks for a more rigorous treatment. And important thing to note is that the dependence or independence of these columns. So when we notice that are these three columns independent? or can one be obtained as a linear combination of any other? So if I just label them as C1, C2, and C3, you will notice that C1 plus C2 equals C3, or C3 minus C2 equals C1, or even C3 minus C2 minus C1 equals C2. So any two are independent, but one column is always dependent. Thus, since we have independent columns equals 2, the column space of A, denoted by CA, is a two-dimensional subspace of R. How much will it be 2? No. So this superscript that goes here is actually determined by the number of rows. Because in a rudimentary sense, when we are dealing with any vector which has say a few components, the number of these components is what goes on top here, and that is denoted usually by the number of rows because we treat vectors as say column matrices, and so it's a two-dimensional subspace of R4. This dimension, as we'll define further, simply means the number of say elements in the subspace. Okay, that might not be true because the subspace contains much else. It is spanned by all of these. But yeah, this is actually the number of independent columns or the basis. So number of elements in the basis of this subspace. What is the basis? Again, we'll examine in the upcoming slides. Now, similarly for the null space. So one way to think of the null space is that it tells us how to combine the columns or how to come up with linear combinations of the columns to get a zero vector. So formally, of course, the null space contains all solutions to the system Ax equals 0. And how can we look at it? So again, let's go back to our original matrix. And we are trying to solve for the system Ax equals 0, which would imply that I'm looking for these x's now, which will constitute my null space. And so I'm looking for, say, these elements x1, x2, and x3. Remember, because this is 4 cross 3, this has to be 3 cross 1, which will yield zeros on the right hand side. So, of course, as we discussed, I mean, just off the top of our heads, x equals 0, or I mean, all x1, x2, x3 equals 0 is, of course, the solution. But is there any other? I mean, can we think of one more? So, remember how we looked at matrix multiplication as multiplying each of these elements once and combining the columns from matrix A. So you will find that even say x1, x2, x3 equals. So I add the first two and subtract the third column. So I add the first two columns and subtract the third, and I'll end up with 0. Or even say any other such combination which produces the same result. So say you subtract the first and the second from the third, and you still end up with zero. All of these are solutions. And of course, the thing you'll notice is that any multiples of these will also be solutions. So need not be one. It can be say some minus 17, minus 17, 17, as long as the ratios are one, or say more generally, it's C 1, 1 minus 1, where say C can be any real number, negative, positive, even zero. So that will include this zero solution as well. So the general solution for this is any scalar C times 1, 1 minus 1. And this is in fact a line through R3. Is the null space a subspace? Uh, can we check? So when I say subspace, of course, I mean the vector subspace because we're dealing with vectors here. So we remember the properties. So the first condition is that if V and W lie in the subspace, then the combination say V plus W must also lie. So if V and W lie in the null space, then by definition of null space, AV equals 0 and AW equals 0. So when we look up for the element V plus W, so we already looked at the associative properties of matrices in our previous session. So this breaks down to AV plus AW, which again individually is 0. So this is 0. So indeed AV plus W is also 0. Thus this also satisfies the definition of null space. So the first property is indeed satisfied. Onto the second one, that any scalar multiple, say if V is an element, then any scalar multiple of this vector should also lie in the same subspace. So this is the definition of the null space. If I apply it to this scalar multiple of the vector kv, then again from last week we looked at how the scalar multiplication works for matrices. So k can indeed be pulled out and I can have AV inside. But this term I know is 0. So this is k times 0 is 0, which again fits the definition of the null space. So this condition is satisfied as well. So we see that the null space is indeed a subspace. Okay, now on to a few more definitions. So we'll discuss the span, the basis, and the dimension of a vector space. First, the independent columns of A. So if all the columns are independent, then the only solution to the homogeneous system Ax equals 0 is x equals 0, and the null space is Z. Z, as we had discussed, is the one-dimensional null space containing only the zero vector. This is when all the columns of A are independent. If any are dependent, then the situation changes, of course. We have other solutions and other elements lying in the null space. Now, in independent vectors, so last week we had a check for independent vectors and we also defined them. So for any set of vectors v1, v2 up to vk, they are independent if and only if the only linear combination that produces zero. So say a set of vectors v1, v2 up to vk, is linearly independent, if C1 V1 plus C2 V2 plus CK VK is 0 only for C1 equals C2 equals C3 equals CK equals 0. So the linear combination of these vectors will yield 0 only when all the coefficients are individually and simultaneously 0. In all other situations, the linear combination will not be 0. And should a set of vectors satisfy this property, then they will be called linearly independent. Now, any matrix with m less than n has dependent columns, and thus at least n minus m free variables or special solutions exist. The vectors v1 till vk span the space of S if S contains all combinations of the v's. The vectors v1, v2, and so on till vk are a basis for S if A, they are independent, and B, they span S. These are the two criteria. The dimension of a space S, so as we were discussing, is the number of vectors in every basis for S. So while there might be multiple basis sets, the dimension will be the same. That is, the number of elements in each of these basis sets will be the same. However, the basis set is not unique. If A is 4 by 4 and invertible, then its columns are a basis for R4, and the dimension of R4 is 4 again, since the number of elements in the basis is 4, which is actually the 4 independent columns. Now, the way a span is defined is that a set of vectors spans a space if the linear combinations fill the space, and the columns of a matrix span its column space. That is, the column space is comprised of the linear combination of the columns. They might be dependent. Similarly, for the row space of a matrix is subspace of Rn spanned by the rows. And another way to look at it is that the row space of A is simply the column space of its transpose. Very obvious, of course. Now, the basis for any vector space is a sequence of vectors with following two properties. One is that the basis vectors are linearly independent, and second, they span the space. We'll use these two criteria to find basis for a few example matrices we'll discuss. And every vector V in the space is a combination of the basis vectors because they span the space. And the combination that produces V is unique because the basis vectors are independent. Thus, there is one and only one way to write V as a combination of the basis vectors. While the basis vectors themselves may not be unique, that is, for the same set of vectors, you may come up with multiple basis vectors. Once your basis vector is chosen, the way to define or to express any vector in that space will be unique for the chosen set of basis vector. And the vectors v1 till vn are a basis for Rn exactly when they are the columns of an n by n invertible matrix. When the columns are dependent, we keep only the pivot columns, and the first two columns will be above. Okay, so this I think deals with some specific matrix. The pivot columns of A are a basis for its column space, and the pivot rows of A are a basis for its row space. The dimension, as we discussed, in is the number of vectors in every basis. See how it says every basis, because again the basis is not unique. There might be many of them, and the dealing with some numbers here. So the column space CA and the row space C of A transpose both have the dimension R, which actually equals the rank of the matrix. The null space has the dimension n minus R, that is number of columns minus the rank. We also looked at this rank nullity theorem in our previous session. The left null space N of A transpose, or simply the null space of the transpose of A, has the dimension M minus R, because when we transpose A from M cross N to A transpose, which is an N cross M system, M is the number of columns. So more generally, it will be the number of columns minus the rank. Now, elimination produces bases for the row space and null space of A, and they are the same as for R. R, of course, being the reduced row echelon form. Elimination often changes the column space. This is something we discussed, and the left null space. However, the dimensions remain unchanged. So, should we elect to perform, uh, say, elimination, and we want to extract a basis for any given system? One way to do it would be to put any given vectors as the rows. Another way would be to put them as columns and then perform elimination. Both ways are acceptable. However, we must keep in mind that elimination changes the column space. That will affect the final choice of basis vectors. We'll also look at it in an example. The four fundamental subspaces, of course, are the row space, which is the column space of A transpose, the column space of A, the null space, and the left null space. Here also we have a few key ideas, as you will see in this box to the right, which says that independent vectors suggests that no vectors are extra. All the vectors are unique and there is no vector which can be expressed as a linear combination of the others. Spanning a space suggests that there are enough vectors to produce the rest, or that I can express any vector in the space as a combination of a select few. Thus, they are said to span the space. The basis for a space need not be too many, and they cannot be too few. They must be exact. And the dimension of space is the number of vectors in a basis. The dimension of the row space is the rank R, and the non-zero rows of R from the basis. R is the reduced row echelon form of any given matrix A. The dimension of the column space is the rank R, and the pivot columns form a basis. The null space has a dimension n minus r, that is the number of columns minus the rank. And if A is m by n of rank r, its left null space has a dimension m minus r, because the left null space deals with A transpose. The fundamental theorem of linear algebra, which again comes in two parts, suggests that the column space and row space both have the dimension r, and the null spaces, that is both the null space and the left null space. So the null space has a dimension n minus r, and the left one has the dimension m minus r. Another topic that we touched in this week was the method of least squares. And the way to visualize is that say given a few data points, you want to fit a linear function in between them, which will help you say extrapolate or interpolate between the given data points. And you want the error from your approximation to be minimum. And so you want to fit or you want to have a line of best fit. So given a few data points such as x1y1, x2y2, xn, then when we try to fit a line such as y equals mx plus c or fx equals ax plus b, and the way to optimize this fit is to minimize the error. The error is measured between, for every xi, we have a y corresponding yi, and the yi minus the you have sorry. So yi would actually refer to the actual given value, and you calculate a value of your function, or you evaluate your function at this point. So the difference between your function, the value of your function, and the given data point is the error, and you sum up these errors over all of these discrete points, and you minimize that sum. And of course, when we say minimize, we have all learned calculus. Straight up, uh, we try to say apply principles of calculus. We calculate the derivative and set it to zero. And here we are trying to work out these coefficients a and b. So we take partial derivative of this error function with respect to a and b, set it to zero, and the expressions that we come up with, in fact, in matrix form, are the one that have been touched upon in the lecture. So this matrix expression is in fact equivalent to the one we obtain after applying principles of calculus and setting the partial derivative to zero. And once we arrive at this form, the solution to this can be found as simply we multiply the left and right hand sides by the inverses. So A transpose A whole inverse will leave only LHS X, and the solution is X equals A transpose A whole inverse A transpose of Y. And X is the least square solutions for the overdetermined system 1. And X, of course, gives us the coefficients A and B for our function Ax plus B. Or as you can see, this is simply the equation of the line Mx plus C. We'll look at an example for a given data set and try to say determine the best fit line. Another concept that was touched upon this week was had to do with projections and orthogonalization and orthogonal systems. And one key area where this orthogonalization is used is actually to produce an orthogonal basis for any given vector space from a given set of vectors. And the way to do it is called Gram-Schmidt orthogonalization. And I have the algorithm here. So suppose you are given any set B containing of three vectors u1, u2, u3, which you already know is a basis for R3. So to be a basis, they must be independent, linearly independent, and secondly, they must span the set B. So once they are the basis, we can have an orthogonal set B prime uh, consisting of elements v1, v2, v3 such that v1 is same as your original element u1, you leave it unchanged. Second element v2 is actually u2 minus the projection of u2 on u1, uh, the projection of u2 on v1, which is the same as u1, and this will be along a unit vector in the direction of v1. And the third vector for the basis v3 will be u3 minus the projection of u3 on a unit vector along v1 minus the projection of u3 on a unit vector along v2. Projection, of course, here is denoted by this dot product. Should you express it in matrix form, you will have, say, transposes here because, say, your U3 matrix is like U31, U32, U33. Your V2 matrix is, say, U V21, V22, V23. And when you want to multiply this, of course, this is not acceptable. This is 3, 1, this is 3, 1. But I can multiply the transpose, and this is perfectly okay. So now it is 1 cross 3, 3 cross 1, and I'll end up with a 1 cross 1 or simply a scalar. And thus I will write this as U3 transpose times V2. When I'm writing it as vectors, I simply use the dot product and the meaning is inherent. So we are obeying all the laws of matrix multiplication. And like we discussed, for any basis B of Rn, it neither does it need to be orthogonal, nor do the basis vectors need to be unit vectors. In fact, any linearly independent set of n vectors can serve as a basis given that the elements of the basis are linearly independent and they span the given set B. And one very simple example, like I was asked to clarify on the concept of a basis, and I said that for R3, The basis vectors can simply be your I hat, j hat, and k hat. So 1 0 0 0 1 0 1 0 0 0 1. So the set of these three vectors comprises the basis. Now they are unit vectors as well as they are mutually orthogonal, but that need not be the case all the time. And here it is shown that for the same vector space R3, 1 0 0, 1 1 0, and 1 1 1 also constitute a basis. They are linearly independent and they span the set. So B is not an orthogonal basis, but it does not have to be. And the key advantage of an orthogonal basis, or why we go through all of this trouble to actually establish an orthogonal system or an orthonormal system, is because it's the most convenient basis for V. And one of the advantages that any orthonormal basis will have over any other basis is the comparative ease with which we can obtain the coordinates of vector u relative to the basis or simply express any given vector u in that space. So we have touched on the concepts. We'll take a short break and then we'll solve a few illustrative examples. Hi, welcome back, and let's resume our session. So, I did look at the assignment questions from this week, and I found that they were rather straightforward in terms of the concepts that they, let's say, sought to reinforce and the way they could be solved. So, most were, say, direct questions. If you knew the relevant theorem or if you knew the relevant properties, you could work out the answers pretty easily. So, the sort of questions that we'll be going over today are say more of a more fundamental and illustrative nature, and also rather than being multiple choice questions, they would involve a lot of math. So let's get started. The first question has given us two vectors, x1 equaling 0, 1, 3 and x2 equaling 2, 4, 0, and it deals with subspaces. So the first part, find v1, which is actually the subspace generated by x1. Find v2, which is the subspace generated by x2, and describe their intersection. One disclaimer, so when I say generated or when the question says generated, it means that the smallest subspace that contains x1. Similarly for x2, so the subspace generated by x2 is the smallest subspace which contains itself. Again, when it's a subspace, it has to obey the qualifying criteria or the properties of subspace. And one way, of course, a very useful thing would be to actually visualize this question. So since we are only in three dimensions, we are still in R3 because the number of components are three. So we can still draw this and in a right-handed system. So the first vector is 0, 1, and 3. So maybe somewhere here, this can be x1. And the second is 2, 4, 0, 2, 4, and 0. So maybe here, this can be x2. Now we have to find firstly the subspace generated by x1. So just to revise the properties of subspaces, the two important properties are first, any linear combination of say two vectors of the subspace must in turn lie in the same space. The second property being any scalar multiple of a vector in this space or vectors of this space must lie in the same space. So let's look at x1. Say if I have a linear combination, let's go the other way. So if any multiple of x1, so any multiple of x1, say twice x1 would be maybe here. Negative of x1 would be on the other side, maybe here. And in general, any scalar multiple of x1 will simply lie along the line containing x1. So maybe if I use a different color, so this line did not pass through x1 for some reason. This line, which of course extends indefinitely on both sides, that contains x1 will also contain any scalar multiple of x1. At the same time, any linear combination of x1. So say you have x1 plus 0, that is very critical. So it must pass through the origin. x1 plus minus x1 would in turn be 0, x1 plus 2 x1 would be 3x1 and so on. All of it would lie on this very line. So the subspace generated or the smallest subspace that contains x1 is a line containing x1 and passing through the origin. So this may be thought to be as v1. Now similarly when we look at x2, the same concepts apply. So any say any scalar multiple of x2, say 2x2 might be somewhere here, minus x2 or minus 2x2 might be somewhere back here. So similarly for any linear combination of x2, like x2 plus minus x2 equals 0, x2 plus 0 equals x2 and so on, must lie along this line that contains x2. So if I use the color green here, so the straight line containing x2 and passing through the origin. Why is passing through the origin important? Because otherwise, if you have the linear combination, say x2 plus minus 1 times x2, this will equal 0. If your straight line does not contain or doesn't pass through the origin, then this linear combination is no longer contained in the same subspace. Thus, your line will cease to be a subspace of the given vector. Thus, v1 and v2 are the subspaces generated by the given vectors. We must also comment on their intersection. So what is v1 intersection v2? And since these two spaces are just lines, their intersection, I'll just write it here. So the subspaces are lines, intersection of two lines is a point, of course. Which point is that here? So that point is nothing but the origin. The intersection of the subspaces v1 and v2 is nothing but the origin. Is origin itself a subspace of R3? So let us check. Is origin or the zero vector a subspace of R3? So A0 B0 is 0, which lies in 0. A times 0 is again 0, which lies in 0. So yes, this is satisfied. So we have shown the two subspaces and we have described the intersection, which is nothing but the origin or the zero vector. Now, the second part of this question, find V3, which is actually a subspace generated by x1, x2, and is V3 equal to V1 union V2. So, okay, I'll just draw it again. And this is not to scale, so do excuse me. This was x1, this was x2, and the spaces. So this is V1, This is V2. And the question now posed to us is find the subspace generated by the set containing the elements x1 and x2, and is V3 equals to V1 union V2. Now, when I say V1 union V2, it is just these two lines. So it is just this line here and this other line here. But what is a subspace generated by a set which has x1 and x2 as its elements? Again, when we are talking subspace, we look at the two inherent properties. So any scalar multiple. So if we are just looking at the union, so these two lines, if I have any scalar multiple of x1 that lies on this line v1, any scalar multiple of x2 lies on the line v2. So scalar multiple condition is satisfied for the union. But what about the condition on linear combinations? Say even if I took the simplest linear combination, which is just x1 plus x2. So these are vectors in three space. I can visualize them, I can add them, I can use the parallelogram law. Easy to visualize. And this will be x1 plus x2. I mean, straight away we see that it does not lie on the union of v1 and v2, because v1 and v2, the union of it is just these two lines. And the linear combination does not, in fact, lie on either of these lines. But where does this linear combination lie? Or in general, where will any of these linear combinations lie? So a little thought will tell us that, in fact, it will lie on the plane spanned by these two lines. This plane will contain, and of course, it passes through the origin. I mean, that's by default because it is spanned by V1 and V2. V1, V2 themselves pass through the origin, but stating it just in case and perhaps to reinforce the point. So this will contain V1, this will contain V2. It is spanned by V1 and V2, and of course, it contains all possible linear combinations of x1 and x2. So the plane spanned by V1 and V2 and passing through the origin is in fact our subspace V3. Is V3 equal to V1 union V2? Nope. No, V3 is not equal to V1 union V2. In fact, V1 union V2 is just a subset of V3. There's another question to be answered here. Find a subspace S of V3 such that x1, x2 does not belong to S. So we have this subspace V3. Of this subspace, we are asked to find another subset S such that neither x nor x1 nor x2 belongs to this given subset. So it can be any subset. We have a plane, so we can have any say, small region defined by any mathematical conditions also. Of course, one straightforward thing which I see right here is x1 plus x2. So the subspace x1 plus x2, or in fact any linear combination, say c1 x1 plus c2 x2, does not contain either x1 or x2. So it can be a possible candidate for S. Of course, this is not unique. You can come up with your own subspace. Now, the third part asks, what is the intersection of V3 with the xy plane? V3, as we saw, is a plane. XY plane is, well, of course, a plane. And the intersection of two planes usually gives a line unless they are parallel. Then the intersection is null. If they're parallel and coincident, then the intersection is the whole plane. What can this line be? So when I say the xy plane, the z coordinate is 0. And can we think of a vector here which has a 0 z coordinate? It's given in the question itself, x2. So x2 is actually a line in the xy plane, and we have generated a subspace V3 which contains x2, which thus x2 is contained both in the xy plane and in our subspace V3. So the intersection of this subspace with the xy plane is very simply the line containing V3, containing x2, which is in fact our subspace V2. So visualization helped in this case. We could draw and get a feel of the question. However, that was only possible because this was a question in R3. When we extrapolate this to further dimensions, visualization becomes difficult. However, the fundamentals and the governing principles remain the same. The second question has to do with a best fit line or fitting a linear function through a given set of data points. So we already looked at the mathematical formulation. I'll just get started with the question directly. So the way to do it is that we write these functions as, say, f of x equals ax plus b, or some yi equals axi plus b, and we try to find suitable coefficients a and b, or suitable parameters a and b. So in this case, uh, let us again say assume the function y equals ax plus b. For these various data points, what we end up with is 1 1, y equals 1 equals 1, uh, sorry, y equals a1 plus b, 3 equals a2 plus b, 4 equals, so remember I'm just working with these individual data points. So this is corresponding to data point 1 1, this is corresponding to 2 3, this is 2 3 4, and so on. So 4 equals a 3 plus b. Similarly for 4 6, we have 6 equals a4 plus b, and for 5 5, 5 equals a5 plus b. Now we are dealing with matrices. Of course, we would like to write this in matrix form. The LHS is, well, pretty simple: 1 3 4 6 and 5. What about the RHS? So as we said, we are trying to find these parameters a and b. So the unknowns in this case are simply a and b. And when I try to put this in matrix fashion, I notice that the uh, elements of this blank matrix will be what? So I have A1 plus B, so this simply is 1, 1. I have 2A plus B, so 2, 1. I have 3A plus B, so 3, 1. The second column is simply 1. It contains only ones, and the left one has 1, 2, 3, 4, and 5. So this is of some form y equals ax, where x in this case contains the unknowns, which are the parameters a and b. So we know that the solution, as we saw, yes, the solution is given as x equals a transpose a whole inverse a transpose times y. So we must compute transposes and inverses. So this is a. A transpose is of course 1, 2, 3, 4, 5, 1, 1, 1, 1, 1. A transpose A is 2, 3, 4, 5, 1, 1, 1 times 2, 3, 4, 5, 1, 1, 1, 1, 1. This is 2 cross 5. This is 5 cross 2. The system I'll end up will be 2 cross 2. So this shall equal 1 into 1 plus 2 into 2 plus 3 into 3 plus 4 into 4 plus 5 into 5. And the second element will be simply be 1 into 1 plus 2 into 1 plus 3 into 1 plus 4 into 1 plus 5 into 1. This element right here will be 1 into 1 plus 2 into 1 plus 3 into 1 plus 4 into 1 plus 5 into 1. This one will simply be the product, sum of products of 1. So 1 into 1 plus 1 into 1 plus 1 into 1. And what does this turn out to be? So this is 1 plus 4 plus 25 plus 16. This turns out to be 55. This is 12, 315. These are the same. This is 15 and this is simply 5. So this is A transpose A. I must also find the inverse of this. So since this is just a 2 by 2 matrix, I'm doing it by hand. If it were larger, we can simply resort to using our calculators. In fact, soon we won't even be needing to do these calculations by hand because we'll look in more into the aspects of how these principles and these techniques are implemented in a code. But for now, this is what we must do. So for a 2 by 2 system, we know that this is simply 1 by det A, and here we'll simply switch the diagonal elements and have a negative sign on the off diagonal elements. So this will be 5 minus 15 and 55. The det of A of course is 55 into 5 minus 15 square. So to take out 5, so 5 times 5, 25. If you have 5, 5, 3, 3, okay, 25. This is 11 into 1 minus 3 into 3. So 11 minus 9 is 2. This is 50. So this is 1 by 50 times 5 minus 15 and 55. Just look again, what is the solution? Is A transpose A whole inverse A transpose Y. So X is A transpose A whole inverse A transpose Y. I have calculated A transpose A inverse. So for X, I'll just multiply all these at the same time. So A transpose is again 1, 2, 3, 4, 5, and 1, 1, 1. So 1, 2, 3, 4, 5. And the Y matrix is 1, 3, 4, 6, 5. Let us just check for consistency. So this is 2 cross 2, this is 2 cross 5, and this is 5 cross 1. So I multiply this first. You can go in any sequence. I think they should end up to be the same. And this is 2 cross 5 and 5 cross 1. So the product matrix will be 2 cross 1. So 1 into 1 plus 2 into 3 plus 3 into 4 plus 4 into 6 plus 5 into 5. This will be 1 into 1 plus 1 into 3 plus 1 into 4 plus 1 into 6 plus 1 into 5. So this turns out to be 25 plus 24 is 49. 49 plus 12, 49 plus 10 is 59, 61. 61 plus 6 is 67 plus 1 is 68. And here I have 5 plus 6, 11 plus 4, 15 plus 3, 18 plus 1, 19. This is 2 cross 2, this is 2 cross 1. The product will again be 2 cross 1. So this turns out to be 68 into 5 minus 19 into 15. And the second turns out to be 6 minus 15 into 68 plus 19 into 55. And turns out this will be 55 and 25. And we divide both of those by 50. So we'll have 55 by 50, 25 by 50. This turns out to be 1.1 and zero point 0.5. Thus our function is in fact 1.1x plus zero point 0.5. This is the least square length, or we can also write this as y equals 1.1x plus zero point 0.5. And just as a good measure, we can also compute the error. So the sum of the square errors. It will turn out to be, so for every given value of y, you obtain the, you subtract the value of the function at the given value of x and square them to compute the error. So for uh, y1, this is y equals 1 and the value of the function at x equals 1 plus for y equals 3, the value of function at x equals 2 and so on. Remember, this is because our data points are 1, 1, 2, 3, 3, 4, 4, 6, and 5, 5. So I've put the x here and the y here for each case, and so on. And this will in fact turn out to be 1 minus 1.6 square plus 3 minus 2.7 square plus 4 minus 3.8 square plus 6 minus 4.9 square plus 5 minus 6 square. And this turns out to be 2.7. In fact, this is the least amount of error you can generate while fitting any line through these data points. Does the line pass through all of the data points? No. Does it pass through any of the data points? We can definitely check. There is a good chance it might not. But on average, will the error of this data of this fitting, that is the sum of the squares of the distances between the given data points on this line, will it be the minimum? Yes, you are guaranteed. So this is the best fit line we obtained. The third question talks about finding the basis and the dimension for a vector space. So I think this should have been inverted because the dimension is simply the number of elements in the basis. So anyway, we first have to find the basis, only then we can comment on the dimension for a vector space which is spanned by these vectors. So you are given four vectors, say u1, u2, u3, u4, which span a vector space. And on the basis of these given vectors, you are asked to comment on the basis for that space. In fact, you have to determine or find a basis, and you also have to comment on the dimension. So just to recollect the properties of a basis, that first must span the vector space. So any vector of the vector space should be expressible as a combination or as a linear combination of elements of the basis vector. And secondly, the elements or the vectors on the basis should be linearly independent. Now, this first condition is already guaranteed by the question because we are told that these given four vectors, they span the vector space. So this is already taken care of. We should examine the second condition and try to come up with the criteria or try to come up with the dimension. So they should be linearly independent, as we already discussed last week, and we already talked about it today. The way to look for linear independence is to arrange these vectors in the rows of a matrix to perform elementary matrix operations and eliminations, and to actually end up with the reduced form or the row reduced form. So let's do that. We'll arrange these vectors in a matrix. So 1, 1, minus 2, 0, and minus 1. 1, 2, 0, minus 4, and 1. 0, 1, 3, minus 3, and 2. 2, 3, 0, minus 2, and 0. Sorry about that. And now we aim to perform eliminations and to obtain the row reduced form of this matrix. So let's do that. We will leave the first row unchanged. Second row can be transformed as R2 minus R1. So 1 minus 1 is 0, 2 minus 1 is 1, 0 minus 2 is plus 2, minus 4 minus 0 is minus 4, and 1 minus minus 1 is 2. R3 already has a 0 in the first column, so we leave it untouched. R4 changes R4 minus twice R1 as you want to eliminate this element right here. So 2 minus 2 is, so first writing the third row as it was. For the fourth one, 2 minus 2 is 0, 3 minus 2 is 1, 0 minus minus 4 is plus 4, minus 2 minus 0 is minus 2, and 0 minus 0 minus 2 is 0 minus minus 2 is 2. Okay, now we continue. So now we would like to eliminate these elements while keeping R2 untouched. So the next set of operations can be R1 is untouched. So 1, 1 minus 2, 0 minus 1, 0, 1, 2 minus 4 and 2. Now R3 minus R2, and similarly for R4. So this will be uh, 0 minus 0, 0, 1 minus 1, 0, 3 minus 2, 1, minus 3 plus 4 is 1, 2 minus 2 is 0, and 0 minus 0 is 0, 1 minus 1 is 0, 4 minus 2 is 2, minus 2 plus 4 is 2, and 2 minus 2 is 0. And already we can see that the fourth row is actually simply twice the third row. So we'll end up with zeros in the fourth row. So 1, 1 minus 2, 0 minus 1, 0, 1, 2 minus 4, 2, 0, 0, 1, 1, 0, and R4 goes to R4 minus twice R3, so 0 minus 0, 0, 0 minus 0, 0, 2 minus 2, 0, 2 minus 2, 0, and 0 again. So this is the last one is a row of 0, so not very useful or helpful. But we have three non-zero rows, which again are linearly independent, and the basis is constituted by these three. So the basis is constituted by 1, 1 minus 2, 0 minus 1, 0, 1, 2 minus 4, 2, and 0, 0, 1, 1, 0. So the basis has three elements. What can we say about the dimension? Dimension is simply the number of elements in the basis, which is 3. So the dimension is 3. Now we use the three non-zero rows from this reduced matrix R. Would we have used the three rows from the original matrix? Well, definitely yes. However, it is important to note that see often during elimination we end up switching rows in case the pivot element comes out to be 0. And so we must keep a track of the correspondence, that is which row are we switching, and the same row should be taken into account for calculation of the basis. So say if I switched in some of these elimination steps and ended up with these rows. However, originally these correspond to say this corresponding to 1, this to 4, this to 3, and this to the third row. Then from the original matrix I must pick 1, 2, and 4. That must be kept in mind. Otherwise it's easy. And I also tried doing this with the columns, and this is what I got. So had we arranged the given vectors as columns of a matrix, say something like 1, 1, minus 2, 0, minus 1, 1, 2, 0, minus 4, and 1, 0, 1, 3, minus 3, and 2, 2, 3, 0, minus 2, and 0. If this was the matrix we arrange the given vector into and perform again elimination, then what we would have ended up with would be 1 0 0 0 0 1 1 0 0 0 0 1 1 0 0 and 2 1 2 0 0. And here we see that we have pivots in these three columns. So these will be our pivot columns. But can we use these three columns as the basis? Now, one thing which will definitely catch our eye in the very first place is look at these rows of zeros here. What my basis should do is my basis should span the vector space. So every vector in that space should be expressible as a linear combination of elements of my basis. We have these vectors here which have this fourth and fifth components non-zero. But do you think any combination of these columns will end up having these fourth and fifth components as non-zero? Never, because they are zero. So these, say the columns we end up with after elimination simply cannot be used in the basis. But these pivot columns, their corresponding columns in the original matrix, can they be used? Yes, and this is also something we saw from arranging these columns, arranging these vectors in rows. So this is something that has to be kept in mind. And this has happened because, as I said, the column space has indeed changed. So just something to remember for future exercises. The fourth question is asking us to find the incidence matrix for the given graph. So during the lectures, Professor Day briefly touched at the incident matrix for any given network or any given graph. So this is a similar example. And just to recollect, I mean, the fundamental idea of an incidence matrix is that it encodes how the nodes connect to the edges, or how the edges connect the nodes, how the nodes are connected to each other, basically to do with the connectivity of the system. And the number of rows equals the number of edges. This is for the incidence matrix, and the number of columns equals the number of nodes. Again, the way to fill up this matrix is that, say, for an edge that is row for our understanding, connecting node I to node J, we fill -1 in column I and +1 in column J, and all other entries are 0, or to suggest that they do not interact amongst themselves. So I'll just redraw this here. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. They are connected. I'll put the arrows. So this is our edge 1. This is edge 2. This is 3, 4, 5, and 6. Directions are important because, of course, they'll dictate the sign of 1, whether it's a +1 or a -1. So let us construct the matrix. So the number of rows will be the number of edges. Here we have number of edges is 6. So the number of rows will be 6. Number of nodes is 5. So number of columns will also be 5. These are 6 rows. And 5 columns. So this will say correspond to node 1, node 2, 3, node 4, and node 5, while the rows will correspond to edge 1, edge 2, edge 3, edge 4, edge 5, and edge 6. Now we must set about filling this matrix. So what can we say about the first edge? It connects node 1 to node 2, leaves from node 1 and goes into node 2. So for 1, as I said, for an edge connecting node I to node J, or I think a more clear way would be to say going from node I to node J, we put -1 in I and +1 for column J. So edge 1 goes from 1 to 2. So for the column corresponding to node 1, we put -1. For the column corresponding to node 2, we put +1. For edge 2, it goes from node 2 to node 3. So in the row corresponding to edge 2, which is this, for the column corresponding to node 2, we put -1. For the column corresponding to node 3, we put +1. Edge 3 goes from node 1 to node 3. So corresponding to node 1, we put -1. Corresponding to node 3, we put +1. The edge 4 goes from node 2 to node 4. So corresponding to node 4, 2, we put -1. And corresponding to node 4, we put +1. Edge 5 goes from node 4 to node 5. So under the column corresponding to node 4 -1, column corresponding to 5 +1. Similarly for 6 goes from 5 to 3. The other columns will be filled with zeros. And this is our incidence matrix. This was rather straightforward to find, but we should take a moment here to think what this matrix actually signifies. So say if I say put it as a system AX equals 0, just for the simplest case, a homogeneous system where A is this matrix. So I will have something like say minus 1, 1, 0, 0, 0, 0, minus 1, 1, minus 1, 0, 1, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, minus 1, 1, and 0, 0, 1, 0, minus 1. So this is 1, 2, 3, 4, 5, 6 cross 5. I should have 5 cross 1, so say x1, x2, x3, x4, x5. And I say I write any of these or I just fill them up. So what does it mean? So the first row will actually change to minus x1 plus x2 is 0. The second would be minus x2 plus x3 is 0. Third would be minus x1 plus x3 is 0. Minus x2 plus x4 is 0. Minus x4 plus x5 is 0. And x3 minus x5 is 0. Now, what is x3 minus x5? If we look at it from, say, the perspective of an electrical circuit, or if we draw analogy from an electrical circuit, the nodes can be thought of to have some electric potential, and the difference between potentials of these two nodes can be thought of to be the potential difference. So x3 minus x5 can be thought of to be the potential difference between these two nodes. And for the homogeneous system, where all of these turn out to be 0, we see that this will be satisfied if uh, so one of the trivial solution is of course 0 when all are set to the same potential. But another solution for this, so the null space is what I'm talking about. Another solution to this homogeneous system x equal to 0, x can simply be 1, 1, 1, 1, 1. Or in more general terms, any scalar multiple of this 1, 1, 1, 1, 1. We put all of them equal to each other, and this turns out to be true. We put them all to 0, of course, it is trivially true. But physically, what will it mean? It will mean that if all nodes are at the same potential, there will be no potential difference in between them. And I mean, the system will not really be solvable. And thus, often it's not the potential, but the potential difference we want to work with. So perhaps a way to find some definite solution for the system would be to say ground any one of these, and then we can obtain say unique values or unique solutions for the other. Perhaps in more important terms, maybe this is beyond the scope of this current course, but A transpose Y equals 0 is in fact Kirchhoff's current law, or KCL as we usually refer to it. So this incidence matrix has many uses. I see that we have reached the time limit for this present week. There is one more question I wanted to go over, but maybe we'll look at it in the subsequent week. So any quick doubts? If there are no doubts, then we'll conclude this class. All right. Thank you for tuning in to the week 2 of live sessions for the course Computational Science and Engineering. I am Sourav Goswami from IIT Bombay, and I look forward to interacting with you again next week. Thank you.